Hi, this is Jeff from the Ozark Mountains. That's in Missouri in the USA. Several months ago, we worked on a couple HP digital multimeters from the late 70s, so I thought it was time to get down some more old test equipment from the shelf and see if we can't fix it up. Here we have a Fluke 8810A. This is a 5.5 digit meter from the mid 80s. And if I can point in the camera, there we go. These are Fluke 8000As. These are less expensive units, 3.5 digits. I don't know anything about these. I haven't looked at them yet, so we're going to do it together and try to get through all three in this video, but we'll get as far as we can. Okay, let's jump right in. Thanks to PCBWay for sponsoring this video. They not only do PCBs and flex PCBs, they also have 3D printing service, injection molding service. They do CNC machining, sheet metal fabrication. Head on over to PCBWay.com right now. Check out their 10th anniversary celebration. There are special coupons and drawings. Check them out now. Here is the Fluke 8810A. I always thought this one was neat because it has these piano type keys, and one problem is they stick. See, that's hard. It won't turn on and off now. There, we finally got it. You can get them to stick in between range, and these are kind of the same way. I think this might be a 20 megohm input impedance meter, which is sometimes important depending on what you're measuring. I know it's bit me in the butt before, depending on the specifications of what you're measuring. If it's spec'd for a 10 megometer and you've got a 20 megometer, it can make a difference. On the top here, there is a sticker that says OK. So this probably would have been put on by one of the technicians at the university where this came from. And there's this calibration sticker. And it looks like it says 88 in here. So this probably was before the university bought their own calibration machine, so they could make sure all the units were stayed in calibration. Got the tilting bell here. This thing weighs a ton. Some sort of card edge connector on here. I don't know what that is about. There's another calibration seal, which we'll have to break to get into. And on the bottom, there is a bit of a sticker that kind of gives you some of the basic specifications of the machine. Now, it looks like there used to be some rubber feet here, which are now missing. Maybe they were similar to these, but these seem molded in. Okay, and I reckon to take this apart, we are going to want to take out these two screws, and perhaps the whole back will slide off of it. I want to take a look inside before I plug it in and make sure everything looks okay, and then we'll chance plugging it in and see what happens. Okie dokie, so let's see if we can't get into this guy. Yep, that's going to be difficult to get off there. Okay, I'll pick that sticker off there and then we'll start up the camera again. Well, that took far longer than I expected. I used an alcohol-soaked rag to wet the sticker and worry it off there, as Mr. Miller, my high school librarian, used to say, which just means you work at it for a long time. So this one is a flathead screw, and this one was not a flathead screw, but it should have been. So somebody's definitely been inside before. And I think if I turn it upside down like this, maybe we can get it to slide apart. I don't know, maybe there's some screws in the bail. Maybe I should read the directions. Bit of a different angle here to give me some more working room. What I'm doing is sliding a spudger along the crack in the front and tapping gently with a plastic screwdriver handle. So that puts a little pressure outward like this with the spudger, and the tapping just kind of helps loosen it up. As according to the manual, it just says take out the 2 screws in the back that we took out and slide it apart. So who knows how many decades this thing's been stuck together. So I'll keep working at this, and then when I get it loose, we'll come back. Wow, that thing fought tooth and nail. But we did get the cover off. Slide here out the way. So we have a cover here, and it has all the calibration pots marked. There's some type of weird DuPont style connectors here where it says input voltage. There's some marks right here which have to do with these pots. And it says that there is a fuse under here, I guess. The sides of this are some kind of die-cast aluminum maybe, or maybe pot metal, I don't know. So I think we're going to have to take this cover off to get in here further. Make sure the fuse is okay and make sure the board looks okay. Yeah. That was convenient. It just slips off. Okay, what do we have in here? We've got a power supply section, input fuse. It's a big cap here, a relay. This is all calibration stuff. The inputs. Not sure if those disconnect or not. It's not very easy to pull off if it does. Some CMOS logic ICs. This is marked 7923Q1 C20 or C2506 8600 Korea, and it's got an AMI or AMI marking there. I don't know what that chip is. There's a TTL chip here. Some transistors or op amps probably. Some kind of funky looking package there. Bunch of transistors down here. Okay. And let's get another multimeter out and measure that fuse and see what it says. And you might just be able to see right here, it is set to 115 volts. So this board looks like an add-on board. So I'll have to look in the manual to see what that is for. It's got some ribbon cables going to it, so some type of card edge connector for HPIB. No, I don't know. The one thing is, on the high precision test equipment, you don't want to get your fingers in there touching the board. It's just the oils from your hands will throw things off. I've got the meter on continuity beep. So yep, and our fuse is okay. Nothing on the circuit board looks blown up, so I'll get a power cord connected and we'll try it out. Okie dokie. this has links here. So if you're doing 2-wire or 4-wire measurement, you'd want to set these up differently with them linked together. It's a 2-wire measurement, or you can use a 4-wire measurement, which means that you're providing the current source for the resistance measurement from here, and you're sensing it from here, so you're eliminating any effect that the probes would have on it. And this is the guard circuit connection here, so you can have this connected to some external guard on what you're measuring. So I've got some probes here. I think the easiest thing to try to start with would be a resistance measurement. So before I power it on, I'm going to go K ohms, 200 ohms, so it's got the 20 meg LED on. I don't know if you can hear that high-pitched buzz. That seems to be from the transformer. And okay, I've got the probe shorted. And so that is the overload condition. Okay, so now let me get some resistors to measure, and then we can fire up the bench power supply and do some DC measurements as well. This looks like it might just work and we don't have to do anything. Okay, I got a resistor here out of the box. I measured that with my HP 3478A, which I calibrated at work several years ago. We'll measure it with our Fluke 8810A here. Oh, gotta change the range. $95 ohms. Okay. So it's reading a little low. Huh, that's interesting. It should be reading it here. Yeah, you hear that screeching sound? 93. Yeah, there's definitely something there. Okay, how about a voltage measurement, DC? Okay, I've got it set to DC volts now and auto range. The power supply output is turned off. It's set to 5 volts. It was measuring like 5.025 on the HP meter. Turn the output on. Yeah, 5.00. Okay, so that works. I can turn the supply up to 8 volts. That's doing okay. I also measured a 4.7K resistor, and that worked, but that 100 ohm, this guy seemed to throw it off quite a bit. The other thing I noticed is that, let me shut off the power supply. When this is in resistance measurement mode, you change ranges and that pitch changes. So I wonder, since these switches are sticking, yeah, it's not related to a percussion, you know, the thing bouncing because we're changing the switches. So maybe that's part of the current source generating circuit that's doing that. I don't know. So I think the first thing we'll do is go ahead and unplug this thing and clean all the switches. These mechanically ganked switches always need cleaning after all these years. And then we'll try it again and see if it works any better. I took the front panel loose. There's 2 screws on each side. And you've got to kind of pop it loose from the power switch rail. And carefully wiggle it off there. Mark and unplug these 2 ribbon cables. And I put some rag in here to keep any overspray from getting on the board, or at least reduce it. So here's all the gang switches. Luckily there's access to them. The mode switch is here, and the power switch is actually back here, and there's a rod that activates it. So what I'm going to do is, oh gosh, this thing supposedly has a low, medium, high setting on this nozzle. I don't know that it does it any good, actually. Okay, now with a little cleaner in each one, I'm just going to click each switch, get to repositioned here so you can see that. And I'll do this for a while. I'll clean up the pivot for the power switch here. And I don't think I can squirt anything in the power switch at the back. And I'll pop this back together and see if that made any difference. Okay, I got the front panel put back in there. That's a little tricky. You've got to wiggle it and hold your mouth just right to get all the little nubs on the switches to pass through the circuit board, and the front of the circuit board goes through a little set of protrusions on the back of this. So just got to take your time. I think cleaning those really helped. Everything's snapping into position really nice and easy now. Don't know if it'll work any better, but at least the switches are clean. It's plugged in. Double check that I got the ribbon cables for the front panel plugged in right. They do look right. Okay. Got a set of different probes now, ones that I am more sure on. All right. Yeah, 0.2 ohms resistance on the probes, I would believe that. And if we go to like 20 ohm scale, it's going to read it dead short. Okay. Now, 200 ohm scale. We'll try that 100 ohm resistor. Oh no, this is K. 200 ohms. 9297. Yeah, it definitely needs calibrated. Yeah, these are in 200 ohms, 2K, 20K. That's what I was doing wrong before. I'm sure somebody was yelling at me about it. And this one was, what, 2.7K? Set it to the 20 range. Oh no. There we go. It's 27K. So yeah, that's closer. So the low ohms range needs adjusted. And the voltage was okay. We haven't tried AC voltage yet. Don't really have a good isolated AC voltage source. Let me rig something up so we can try it. Okay, I've got my 10 function generator set up to output about a 4.7, 4.8 volt AC signal at 44 to 45 hertz. So we got this set to AC. Select a little higher than what we think we need. 4.9, 4.89. Okay, so it's not too far off of what the HP was. So this guy definitely needs calibrated, but everything's working now. After cleaning the switches, they're mechanically working better. We don't have that buzzing sound anymore. So that was definitely something in the switch having a dirty contact or slightly shorted contact that was causing some problems there. So what I need to do for this meter, though, is take it to work and calibrate it. Now, the difference between the calibration on this meter, which has all the pots here on it, and the HP right here, is that the HP is all electronic calibration. It stores the calibration values in a non-volatile RAM chip, whereas this one, it's all a bunch of pots, and you've got to go through a very specific procedure and tweak every one of those pots. So either way, the electronic or mechanically tweaking the pots can take a while to get it dialed in right, and you've got to leave the calibration machine on for hours first so it gets warmed up inside. Leave this on for hours, in a relatively temperature controlled environment so you can set it. So I'm going to go ahead and clean the sticky off this lens if I can and get this thing buttoned back up, and we'll have a look at the Fluke 8000s. Okay, curiosity got the better of me, so I pulled this board up. It's just a bunch of logic gates. There's a Dale part here, which I'm guessing is a resistor network. And a little transformer, a couple caps. And mostly it's just CMOS logic. It says DOU assembly 366369. There's no indication of what it does. Oh, this looks like a bridge rectifier. A transformer, bridge rectifier, some type of little switching power supply for isolation, maybe? I don't know. I'll look in the manual and I'll let you know what it is. So it turns out the mystery board is called a digital output unit, and it is a parallel output of the reading on the LED in BCD encoded form. That's kind of interesting. I've seen this on some old panel meters, the mid-late 70s, but never on a multimeter, so it's kind of interesting. Well, here we have our two Fluke 8000As. I just noticed on these that this is serial number 61654 and this is 61748. So they're fairly close in production. Only around, what, 124 off? 126 off? So from the front panel, these both look good. Buttons are a little sticky. This one, the power button, doesn't always want to stick on and it's real slow to release. This one, the power button's a little sticky, but it's okay. Like a lot of other meters like this, it has the fuse right here. And I don't think there's a fuse in this one because that's not wanting to come out. I checked this one and it does have a fuse in it. That is okay. Oh, it does have a fuse in it. Oh, now it's really got a fuse in it. That's awesome. Okay, well, I guess we'll start taking this one apart first. About the only difference between the two is this one has some stuff splashed on the back. And it's rather hard, so it must have been some type of epoxy or something like that. It doesn't dissolve with alcohol. Other than that, they're in about the same condition. So we'll start with this guy. Okay, got you back on the other side now. This one has a flathead screw in here to hold the case together. I think the other one has a Phillips. I'm not sure which is the original. Okay. Rotate the bail around and... oh, that came apart a lot easier than the other one. And of course that's just a big open plastic box. And I'm going to reach across here and grab the probes from the HP 3478A, measure the fuse, and this one might be open. Nope, it's okay. There's just not a good connection on it. And what do we see here? Got a big cap that's kind of out of place. Couple smaller caps. One standing up here on its own. White ceramic chip marked SC409. Our ganged switches. An interesting resistor thing there. And oh yeah, flat flex cable going from here up to the LEDs. I've seen these in other meters before and they're really kind of a pain in the butt. We've got a 7447 which is stuck in a socket and a few other ICs. We got pots here for adjusting it. Got some diodes here. So everything looks okay. It's got one other fuse here, and I'll check that real quick. It's measuring about 11 ohms. Okay, 11.5 ohms, but it's good. So let's see if we can get the current fuse put back in the front here. Gotta hope the fuse sticks in there. It has a couple ears on it, you see there, that go up and down to put it in there. And you push it in and turn it. And it's a bit hokey. It just pushes up against this guy, which pushes up against that metal case right there. I guess both are common. Doesn't seem very sophisticated, but I guess it works. So, okay, good. We've got, see if you can see there. Maybe I'll raise this up for you. Can you see we've got holes in the back of the switches here? So we'll be able to carefully squirt a little bit of contact cleaner in there and work that back and forth. I'm going to prop something under it like this. Try to keep the contact cleaner running downhill. Not sure about this angle. What do you think? It gives me more working room, but I don't think it's as good for you guys. Okay. Now we've got all the squirting done. And some did blow back on the board, so I'm going to have to clean that up really good. And I'm just punching the buttons. They're already snapping much better than they were. Before they were pretty lazy. Oh yeah, so I'll keep doing this and I'll clean the circuit board up and then we'll give it a try. Okay, I've got two resistors here, 330 ohm and a 100K. And I've got the power cord plugged in. Some good probes hooked up, so we'll try turning it on. Well, that didn't seem too promising, did it? One. Okay, we should be in ohms mode. 2. Shorting the leads, we read 0. So I think this is 2K mode. This is 200 ohms mode. So 0.2 for lead resistance, that's reasonable. So 2K, if we measure the 330 ohm, yeah, on the HP it was measuring 330, 331. So this is reasonable for a 3.5 digit. And then for the 100K, to put it in 200K range, 103, and it was measuring over 100 on the HP as well, so that's reasonable. Now let's try the... I'm not sure what that... That seems odd that that number sticks there like that. To read the manual and see what that does, and we can also check the other one and see if it does the same thing. Yeah, we'll try some DC volts next. Okay, I've got the bench power supply set to 5 volts. It measures 5.0023 on the HP 3478A. And we should get something close to that to here. We're in DC volts. And the 20 volt range, kick the power supply on. 5.02, that's respectable. Of course, if we go up to 200 volt range, it's going to be not as good because we're not in the optimum range to resolve that. Okay, now if we go, I just set it to 8 volts. That's reasonable. And I'll turn the output off. Okay, I've got the power supply set to current limit at 100 milliamps. So we should be able to do this. Do DC milliamps. 200 microamps, 2 milliamps, 20 milliamps, 200 milliamps, 2000 milliamps. Okay, so the power supply set to 8 volts, limited at 100 milliamps. We should see about 100 milliamps here. Output on. Power supply says 113 milliamps. And this says 2.1. Yeah, that's not very good at all. It's all over the shop. Oh, there we go. It seems to be if I move that contact we looked at on the back away from that can, it works. So maybe there was supposed to be some insulation in there. 114, 113, that's respectable because the meter on the power supply isn't very accurate either. Okay, let's take the cover off the second one and see if that fuse arrangement is any different. This is the multimeter we were just testing, and this is the second one that we just took apart. And you notice this has a big rectangular can. It has this kind of leaf spring thing that comes up and touches the fuse. And this doesn't seem to be quite right. Maybe it's not the right fuse that's in there. It's too long and it's pushing it back against this can. On this other one, it has an encapsulated fuse holder with a lead going down, and this can is sloped. Here we are missing some footage because I forgot to hit record. So I had tested unit number 2 the same way we did unit number 1, and it worked, except that all 3 decimal points were on at the same time. And I said, well, I'm going to have to go and read the service manual to figure out what controls those. So now we'll pick up at that point. Here we've got the second unit up here again. This is the one that all the decimal points are on. After looking at the service manual, the position of the decimal is entirely controlled by the range switches. There's a set of contacts in there that feed through each other to decide which point should be on. And indeed, if you play with the switches, you can change its behavior. If you get them in just the right spot. See? So I think the problem here is entirely mechanical in the range switches. So we improved them, cleaned them a little bit, but it hasn't fixed it yet. Now let's look at the first one. And of course, one other thing to point out is that in ohms, it displays 1999 for open circuit, not just a random digit in here. So we'll look at the first one again. Okay, here's the first one that we took apart. So if we're on DC milliamps or volts, we get the full display reading 0. But on ohms, we don't. But you notice it kind of, there's a spot where it works correctly. As we press in the switches. So again, I think the problem with this one is also mechanical. It's not making one contact correctly. So what we'll do, let me unplug it here first, is I think we can take the display off here and here, separate this flex board, take this front panel off, this little shield on the bottom, and I'll really hose out these switches with some electronics cleaner, try to flush out anything that's in there, let it dry, and hit it again with the deoxit. I know on other Flukes that have these types of gang switches, it's been a real bear to get the switches cleaned back up like they should be, and I really do not want to have to desolder these switches and take them all apart. So here we're going to start the disassembly of the front panel. Of course, you need to take the fuse holder out. You have to desolder the 2 wires that go up to the other 2 jacks, and then take everything apart very carefully because everything's kind of interlocked. No. And that also lets the red part pop out. Interesting. Okay. Okay, got that shield off of there. We've got bodge wire in there. Had an op amp replaced. And I need to desolder these 2 wires here. Here's unit number 1. I did have it apart. I flushed out the switches with CRC electronics cleaner, squirted in just a little bit of the deoxit, and they all mechanically work fine now, but it didn't take care of that problem with not reading correctly on the LED display when the resistance mode was over limit, open circuit or too much resistance. It couldn't measure it. And then I got to thinking, well, when you're measuring a resistance range of value that it can measure, it works fine. And when I was reading through the manual, it said that it uses two special chips. These two guys right here, U3 is a voltage to frequency converter. They call this the analog chip, and this is the digital chip. And this picks up that frequency and converts it into BCD signals, which get sent down here and decoded to drive the LEDs. So it's like, well, it's probably not the BCD chip because, this digital chip, because it's when it's reading something in the range it is supposed to read, it works fine. So I swapped the analog chip from the other unit, and this one works fine now. I'll show you that here in a second. Problem is you can't find these guys anywhere. This was a special chip made by a company that's now Digilogix, Digitronics. What was the name of it? Siliconics. This was made by Siliconics for Fluke. These two were. And it looks like some have been on eBay in the past, and maybe a few brokers in Asia have a few chips, but I don't think it's worth spending a lot of money to put a new chip in this guy for what it is. And I taped this piece of paper in here to keep the current fuse from shorting against this can. If I do find a chip cheap enough, then I'll 3D print a holder for this. But let's have a look at how it works now. One advantage to needing to take it apart and take this red lens out is that I was able to clean it and polish it and clean the backside where it had gotten dusty over the years. So if we turn it on now, it's reading 1999, we're in K ohm range, 2K. I'll measure the 330 ohm resistor. And it's measuring 0.332K. So, yep, it works fine. But that means the other one doesn't work now. So I'm going to swap the original chip back into this one because the other one has the complete fuse holder. So we'll take a look at it now and see how it's doing. Here's unit number 2. Same thing, took it apart, flushed the switches out, hit them with deoxide again. I've put the U3, the analog chip, back in this one, the good one. And I also had problems putting it back together with all the segments of the display not working. And I found that all of these solder joints right here were cold. I'll put a picture up here. When I hit it with the soldering iron, the solder just rolled off the copper pad. It hadn't stuck there at all. I added a little flux to each pad, soldered it. It took maybe 5 seconds for the solder to flow out nice and stick to the copper. Then I cleaned it up with alcohol. And let's see how this guy works. And this is the one that's got the good fuse holder. So you can see we're on resistance measurement here, and it's measuring open load. I'll connect the 330 ohm resistor. It measures 332 ohms. We're on the 2K range, 200 ohm range. We're out of range again, but you can see the decimal point moved, and we only have the 1 decimal point on now. 20K range. Our decimal points has moved, but we lost one digit because we've got the leading 0. And same here, now we've got 2 leading zeros, so our decimal points moved that way. Now we lost it all together. So flushing the switches out really good on this one took care of that decimal point problem. And this one is a good meter. Everything works really well. Well, I'm pretty happy with this result. All 3 meters actually work. The first of the 8000 A's here has that problem with the resistance range overload indication not working right, but otherwise it measures right. It needs the analog chip U3. The other 2 work fine with a little bit of effort and mostly cleaning the mechanically ganked switches. I'm really happy about this guy working, not only because I like the piano type keys on here, but it's a 5.5 digit meter, so I can set this up with my HP and have another nice benched meter. This one doesn't measure current, but that's fine. I measure voltage and resistance with them most of the time anyhow. So I hope you found this useful. The good thing with this type of test equipment in this era is they release the service manuals with schematics, and there's a lot of people online that have fixed them, and you can find out a lot of information, and it really helps a lot trying to get these guys working again. So Don't be afraid of it. You just have to watch what you're doing. Don't get your greasy paw prints inside the real high precision stuff, and clean up after yourself when you've done some soldering. So, any questions or comments, I would love to hear from you. Leave it in the comment section down below. Thanks to everyone who helps support the channel through Patreon and other means. It's greatly appreciated. There's information about that in the description. And until next time, bye.